Hello, you are watching AP Chemistry, it's actually AP IBHL-1 Chemistry at Allen High School, and we're working on some sample AP questions regarding stoichiometry. So let's move on to our next one right away. This is from way back in 1995, and I'd have to figure out if you guys were even born back in 1995, but we're going to focus right now on the question. We have a sample, and you notice that the sample is a mixture. It is not pure. And so we can't do stoichiometry directly with impure samples. We really need to separate it into pieces. Now, in the first part, it gives us, let's highlight these, we have a 0.2800 gram sample, and it's decomposed. So we're going to see one of the answers to decomposition here in a minute. Even though we haven't learned it, we're going to pre-learn it a little bit. And this clearly tells us that we get CO2 as part of that decomposition, and they give us a pressure and a temperature and ask for grams. Now, hopefully, based on that Tools of the Trade chapter, your mind is already reaching for one of your formula tools. And it's going to be PVNert, but since it asks me for grams, I'm going to be doing a little bit fuller instead of moles. You can always substitute in mass over molar mass for moles. RT, we don't have density. We don't need to worry about that one. And so I'm going to plug in my data to this for part A and solve for my my mass here. So my mass will equal pressure times volume times molar mass. I like to use two M's for that. That's not kind of a universal symbol, over RT. And you can figure out your molar mass for CO2, so that should be readily available. Millimeters mercury, remember, is the same as a torr, so that will direct us to the R we need. Don't forget, you have to have liters when you're dealing with the ideal gas law. So you have to convert those to liters there. And then I would have my molar mass, which is 44.01, 2 oxygens and a carbon. And the R that I grab is the same for torr and millimeters of mercury. We came up with that last time, and it's going to be 62.4. Alternatively, if you like working in one unit all the time, you're welcome to convert your pressure instead if you prefer. And 293 Kelvin. And when we work that out, our mass, I have 0.135 grams. If I did my algebra right, you always want to be checking on me there. Now you notice that this is 3 significant figures, this is 4 significant figures. The temperature really became 2 because we had 273 plus 20, and without that decimal point, this last place is not significant. And then the pressure also has 2, so this really should be rounded to 2 significant figures. So I get 0.14 grams for that. Now let's see what part B asks us. This time it says write balanced equations. For both of them, decomposing, we'll get CO2 from both. And this is not something you know yet, but by the end of the year, we will have worked on our decomposition rules. I actually asked this question on your net ionic lab, and some of you got that pretty well. And so let's take a look at it here. The problem told us we get CO2, and what is left is a metal oxide. And we did that with aluminum carbonate because in a single or in those double replacements, sometimes you see some bubbles forming for CO2. So the rule is that metal carbonates form CO2 and the metal oxide. And remember, just random questions here, CO2 will extinguish a glowing or lit splint because it does not support combustion. So that might have brought a few things back to your memory there. Now, in this case, it said that we also knew that there was this many grams of calcium. So by knowing that, we can figure out what the percent of the calcium was for this problem. So this is when there's a really handy relationship that comes into play. So we need to know the percent by mass. So it's going to be the mass of calcium carbonate over the whole mass of our impure sample. And then it's going to be times 100 because it's a percent. So that's our goal. All right, and we know our mass of our impure sample. That was given in the previous problem as 0.2800 grams. What we have to get at is our mass of calcium carbonate. Now, there's a couple of ways you can do that. You can go from grams of calcium to moles of calcium, and then moles of calcium to moles of calcium carbonate, and then moles of calcium carbonate to grams of calcium carbonate. Or we have a way to do mass to mass within, and that arises from the percent composition formula. So I can take that mass, 0.448 grams of calcium. Now, the mass to mass within ratio comes from the percent composition of calcium carbonate. And it's going to be flipped though. So for every 100.01 grams of calcium carbonate, that would be the whole, so we're doing an inverse there. I have 1 calcium, and it contributes 40.08 grams to that whole. Now, if we inverted this and then multiplied by 100, that's actually a percent composition. What would be the percent composition of calcium within calcium carbonate? All I've done is invert it so I can get my grams of calcium to cancel and end up with grams of calcium carbonate. And it's a little bit quicker than doing this whole string of calculations there. And when I do that, I'm actually at the end of that part, I get 0.112 grams of calcium carbonate must have been present to analyze a sample and find that many grams of calcium. So if you're asked for a mass to a mass within or a mass within to the mass of the substance, you can use that percent composition ratio right there to help with that. Now we can do our percent. We know how much of it was calcium carbonate, so we're going to put that number up here. So that number was 0.0112 grams of calcium carbonate times 100. If we did that mathematics, we'd find that it was 40.0% calcium carbonate by mass. So you might want to be very clear in your communication. Remember, we discussed that before. So that would be our answer to this one. Now, that was kind of a long part. Let's go on to the last part of this question here. And it says, how many grams of the magnesium were present in sample A after it had been heated? So that means we heated this sample, and I'm solely looking at the magnesium portion. We had this formula plus CO2. We're going to heat it and drive off the CO2. And the question is, how much of the magnesium containing product? So how many grams of this magnesium oxide would remain? Now, if I want to get to grams of magnesium oxide, I first need my grams of carbonate. If we do that, we can go mass to moles, moles to moles, moles to mass, using our mole road. So I have to find my starting material. Well, the previous answer gave us that starting amount. Our sample was 0.2800 grams, and we just discovered that we had 0.112 grams of the calcium carbonate. Now, again, if you didn't get that previous one, assume, this isn't the magnesium, this is actually our impure sample, sorry, assume an amount. So this is our sample amount. So now we know our mass of our magnesium carbonate. So we'd have 0.168 grams of magnesium carbonate. To relate it to the magnesium oxide, we need the mole ratio. So we need to get to moles in this case, mass to moles. Use molar mass. You're going to hate that phrase when we're all done with this. I want to get rid of grams and I want to go to moles. And often you are given molar masses, which is really nice. It streamlines our work a little bit. So now I have moles of magnesium carbonate. You want to label the road so that you don't get lost along the way. So if I stopped my calculation, I would be, in my map it said, you are here. So now we want to eliminate moles of magnesium carbonate. And I know you want to skip this step because many of you are seeing that it's a 1-to-1 mole ratio, but don't skip that step. The reader needs to see that you understand that mole ratio concept. So you must include it. And otherwise you're really risking any possibility of maybe partial credit. Now I need to get to grams of magnesium oxide. And I want to eliminate moles. I want to go to mass. Mass to moles, use molar mass. So I'd have 0.30 grams. And my final answer would be 0.0802 grams of magnesium oxide present. Now again, if you're missing a piece from a prior part, assume something reasonable. In this case, you would need to assume something that was less than 0.2800. And you would get credit for part D, even though you'd lost the credit in the prior part. So that's your second AP question, and I look